So here's our simulation of Thomson's experiment, where he's looking at a cathode beam through a cathode ray. So in this simulation, we've got a number of pieces of information displayed for you. We have this little circuit, which you're going to have to answer a question about in the lab. These are parallel plates that are providing an electric field for the cathode ray. You can adjust the voltage of the parallel plates using this slider at the bottom. This is a current. The current can be adjusted, and that's going to change the magnetic field in this region only of our apparatus. Over here, we can see exactly where the particle beam is hitting some sort of measurement tool, which is at the very end of the cathode ray. It's actually supposed to be a fluorescent coating, which is telling you where the beam is hitting. So let's go ahead and get started. I'm going to follow along with your instructions, and you can as well. Like I said, one of the questions on your lab that you're going to fill in is, what is this? This is something we can't adjust in this simulation. It does something important, and you're going to have to figure out what that is. The first thing we're going to do is set the current to 0, which it already is, and we're going to set the voltage to negative 200 volts. Notice how this red outlined circuit is the one that we've just altered. I've displayed the electric field lines in red as well, so you can see right now they're pointing down, and as a result, the cathode beam looks like this. What is the direction of the electric field between the plates? I kind of just told you that. In what direction is the cathode ray deflected? What does this suggest about the charge of the particles that make up the cathode ray? I also want you to look at the trajectory of the ray in this region. What about this suggests that there is no appreciable gravitational field having an effect on the cathode ray? You're also going to record the electric field produced when we set the voltage to negative 200 volts, and I've displayed that down here on your screen. Next up, I'm going to reset the voltage between the plates to 0, and now I'm going to set the current in our solenoid. Remember, you can't actually see the solenoid in this diagram, but it's going to produce a magnetic field just above the region of those metal plates, those parallel plates. So the current I'm going to set is 100 milliamps, positive 100 milliamps. So you can see the green lines right here represent the magnetic field, and this dotted circle is going to represent the outline of our solenoid. So imagine we've got a solenoid that's sticking out of the page. What is the direction of the magnetic field from the solenoid? In which direction is the cathode ray deflected now? What does this suggest about the charge of the particles making up the cathode ray? Based on the direction of the magnetic field, does a positive current mean counterclockwise or clockwise based on this dotted line, which represents our loop, the loops of our solenoid? Assuming the field is being generated in the middle of a uniform segment of solenoid, determine the turns per length ratio, so N over L, for this particular solenoid. Now on to part 1 of the actual experiment. In this experiment, the first thing we're going to do is figure out how fast are the electrons traveling. So Thomson didn't know the charge on the electrons, but he did know that as long as the forces exerted on each electron were balanced, the beam should go undeflected. So what we're going to do in this section is change the current and voltage through a variety of values, record them, and we're only going to record the combination of current and voltage that produces an electric and magnetic field that cause the particle beam to remain undeflected. We're going to define undeflected as having a deflection angle less than 0.3 degrees because it's a little bit tricky to obtain exactly 0-degree deflection using this particular simulation. So here are some values that I've collected that result in, as you can see, very, very little particle beam deflection. So go ahead and pause the video right now, and you can record these values for use in your lab. Now for part 2 of the lab, what we're going to do is determine the charge to mass ratio of the particles. So for this part of the lab, we're going to turn off the magnetic field completely. So no current in our solenoid, no magnetic field, and we're just going to adjust the electric field, and therefore adjust the voltage. So here are some values that I've collected. You can go ahead and pause the video and write these down for your 8 trials for part 2 of the lab.